Yeah, good afternoon. Can you hear me from the last? Am I audible? Yeah. So, what did we discuss in our last lecture? I'm showing you because you are not anyway seeing your notes, right? So I'm only showing the notes, right? So, so what did we do in the backward TD lambda? Backward view of TD lambda. Like, why do we need that first of all? Huh? Because the forward view of TD lambda had is an offline algorithm, right? We have to wait till the end of the episode to make any update in your estimates, right? So what is the main concept we used in backward view of TD lambda? So we introduced this concept of eligibility traces, right? So what is that? Eligibility traces. So for every state, we are maintaining some value called the eligibility of that state. So so that is based on these two things: how recently that state has occurred and how many times that state has occurred, right? So there was some small correction. There was a small mistake in my last class notes. Here, gamma also should be there. I think I wrote only lambda in the previous class. It should be lambda into gamma in the eligibility traces update formula. Okay. So after, so whenever that state occurs, we'll increment. Huh? Okay. I think those who sat initially in the back, they did not respond. Hello. Hello. Am I audible now? Is it better? Uh, so, how are we updating our ET of S? Whenever we visit that state, we are incrementing that by 1. And as time progresses, we are decaying it with this factor of lambda gamma. Okay. So whenever it has occurred, we incremented that, and it will keep decreasing as by multiplicative factor of lambda gamma. And so the update rule of the TD lambda backward is, so you just calculate the one step TD error, which we could have done if we are doing only one step TD. So this is a regular one step TD error. You just calculate the one step TD error, but don't just update your V of ST. You are not updating just V of ST, but you are updating V of S for all states S. And you are you are updating as a function of its eligibility traces as given below. If the state has recently occurred, you are contributing this error more to that state. If it has occurred long back, or if it has occurred very less number of times, the CT of S will be smaller. So the contribution of this error, the attribution of this error to that state will be smaller. Okay. So in every time slot, we'll update all the states with this formula. Okay. As a quick check, we also looked at substituted lambda equal to 0, and we got back our one step TD. Okay. So this is about the TD lambda, and this is about predicting for a given value function, like predicting value function for a given policy pi, right? So we can generalize this to uh, the control problem as well. What is a control problem? Finding the optimal policy, right? For example, SARSA is one algorithm which helps us to find the optimal policy. So we had, if you want to convert, if you want to use similar techniques as eligibility traces for the control problem, we have to make one minor change, which is So maybe I'll come to that. Instead of having an eligibility trace for each state, we have to have an eligibility trace for state action pair. So you maintain a separate eligibility trace for every pair S comma A. So whenever you visit that state pair S comma A, you increase the eligibility trace of that pair by 1, and it will keep decreasing as time goes by, as lambda gamma factor, by factor of lambda gamma. Okay, so that's the main difference. So here for every state we are maintaining an eligibility trace. If you want to implement SARSA using this eligibility trace concept, you have to just maintain one eligibility number for every pair of state action. Okay, for every state action pair, you have to maintain an eligibility trace. So whenever you visit that state action pair, you increment that by 1, and for other state action pairs, it will keep decreasing as a function of the alpha. So that's the main difference. So I have given one reference in the book. I have uploaded in Hello IITK one reference notes, which is like a PDF from the book. So you can look at that PDF where you can see how to use it for Sarsa lambda also. Like whatever we discussed is TD lambda, but by making this small change that instead of maintaining a state eligibility trace for just state, you maintain that for a state action pair, then you can get Sarsa lambda. So you can read from that book as to what are the specific details. But mainly that's the main changes. Otherwise, everything else will more or less be the same. Okay. So that is about the TD lambda backward view, and then we started looking at double Q learning, right? So what is double Q learning? Like why we need double Q learning? To solve this problem of maximization bias, right? So as we have seen, there is whenever you have some random variables and trying to find the maximum expected value, uh, there inherently there is an issue with maximization bias, and we looked at one way to address this, which is about you maintain two estimates of your averages. So you use one set of estimates to decide which is the best term, best action, and use the other set of estimates to find what is its expected value, right? Instead of using all the 100 samples to find the average of your each action, you just use first 50 samples and decide which is the best action to take. And once you decide which is the best action, then you just use another 50 fresh samples of that particular action to find what is uh, the average of that action. So essentially, it boils down to this kind of an issue. Like you maintain two estimates, you find the best, you find which action is the best based on in some set of estimate, and then what is the actual expected value of that you find using another set of estimates. As I said, in double Q learning, that is what we do. We maintain two estimates of the Q function, which are Q1 and Q2. Both are estimates of the Q star. So now in this, instead of using this update rule, we just use this one, which is you decide which is the best action based on the estimated estimate of Q1, and then what is the actual Q value, you just get that from the Q2. So maybe I'll try to quickly show you the algorithm. So this is the algorithm. Just to show you the pseudocode. Here we are maintaining. Here we are maintaining two. Here we are maintaining two estimates of Q1 and Q2. Like both these are estimates of your Q star. And what we'll do is uh, in every step we decide which queue to update. Like we have two estimates, right? In some steps we update Q1, in some steps we update Q2, so that both are reasonably good estimates of your Q star. Okay, so either you do it alternatively or you just throw a coin, and if it lands in head you update Q1, if it lands in tail you update Q2, so that both these estimates are reasonably good and are updated well enough. Okay, so you would have just written here Q1 of S dash comma A dash. Instead of that, you are writing this, where you are getting the best action using Q1, and then you are just finding the estimate of the Q value using Q2. Okay, so you just throw a coin toss and decide which Q estimate you want to update, and once you decide that, you, instead of using this expression in your update, you just get the argmax using one of the queues and the actual value of the queue using another queue. Okay. No, you want to, both Q1 and Q2 should be good estimates of Q star, right? If you just keep updating Q1 always, then Q2 will not be a good estimate of your Q star. No, in every step, you are deciding which one you want to update. So in some time slots, you'll update Q1, in some time slots, you'll update Q2. You're throwing a toss, and if it lands in head, let's say, you update Q1. If it lands in tail, you'll update Q2. Yeah, you are deciding the best action while you are updating Q1. You are deciding the best action according to Q1 and then substituting that estimate of the best action in Q2. I think that will lead to, again, maybe they'll have the same estimates, maybe, right? So if you start from the beginning and you keep updating both of them, maybe both will have the same values. So it's like in the previous example which you have seen, we had 100 samples. What if I use both the all the 100 samples to estimate both U and V? It's similar to that, right? So there will be a lot of correlation between them. So here you are trying to make them independent samples, so that there won't be any correlation. Yeah, this is another thing. Like we are following some epsilon greedy policy, right? So which actions you want to, like which state, like which action you want to behave. Here you can use like, as I said, this is a behavioral policy. The behavioral policy, all that we need is exploration, like infinite exploration. So here you could have used the uniformly random policy, or you could have behaved epsilon greedy with Q. So here it doesn't affect your update as such. So here they are using the best estimate of Q. Like Q1 plus Q2 by 2 is the best estimate of Q, right? So they are just behaving epsilon greedy with respect to Q1 plus Q2 by 2, right? Which policy? Yeah. So finally, the after you converge, the policy will be the arguments with respect to Q1 plus Q2. Okay. Because finally, after everything is done, you can just take Q equal to Q1 plus Q2 by 2 and use that as your estimate of Q. This one, right? This one. Here you are finding which is the best arm according to Q1 and then substituting that in Q2. Otherwise, we would have simply done this. So this is what we would have done normally, where you are also deciding which is the best action according to Q1 and also what is Q1 also you are deciding. So this is same as this, right? You can write this like this, right? Q1 of S dash comma arguments over a Q1 of S dash comma A. So the first term you can write like that, right? So maths over Q of S comma A is nothing but Q1 of S comma arguments over that. Like this first equal to everyone is clear, right? It's just a way of writing the first this expression. So here you are using another Q2, like Q1, Q2. That's the only difference. So that is about, and this is just one small example to illustrate the advantage of double Q learning over the conventional Q learning. Here, this is a small, simple MDP which is given here. Like there are only two states, two non-terminal states, A and B, and so there are only two non-terminal states A and B, and in state A there are two actions, left and right, and they are deterministic. Uh, they have a deterministic behavior. If you take right action, you will go to the terminal state. You will go to this terminal state, and you get a reward of 0. Okay, and if you take left action in state A, again you get a reward of 0 deterministically, and you will go to state B. Okay, and in state B there are many actions possible. Like all these are different actions in state B, and all of them will lead to the same nest state. Like the nest state for all these actions is nothing but the terminal state given here. Okay, and the reward the reward for each of these actions is a stochastic reward, like which is a normal distribution with mean minus zero point 0.1 and standard deviation 1. Okay, it's a Gaussian distribution with this mean and standard deviation. Okay, so from this MDP, intuitively, what is the best policy to follow? Uh, like, what is a policy? Policy is, let's say you are looking only at deterministic policies. The policy is a mapping from your state space to action space, right? So in state A, what is the best action to take? Left or right? How many think left? Right? Because if, on the right, what is the expected reward you'll get if you go right? Expected return is 0, right? You go right and the episode immediately terminates and you get a return of 0, right? So uh, if you go right, you get 0. If you go left, what is the expected return? This is plus 0 plus minus zero point 0.1. Totally, the return will be minus zero point 0.1. The expected reward, the total expected reward will be 0 minus zero point 0.1, which is minus zero point 0.1. So intuitively, it's very clear that the best policy is going right at the state A. So if you do Q learning, eventually it will learn that at A you have to take the right action. So here we are just understanding that here due to this maximization bias which we mentioned, here there are a lot of actions, right? So whenever you are in some state B and you are trying to update the value of going, uh, like you have a lot of actions here, right? So if you do that maths over a q of s comma a kind of an update when you are in some state B, when you are in the state B, this maximization bias will kick in, which will try to overestimate this left reward. So all these left rewards have an expectation of -1, like expected left. All these actions have an expected reward of -1, but due to overestimation problem, the like maximization bias that we discussed, uh, the Q learning might suffer from this overestimation problem and estimate this to be slightly more than minus point one. So it might get maybe if it estimates it to be more than 0, then it might think this is the best action, right? If it overestimates and let's say it thinks of it as point one instead of minus point one, then the best action will look like the left action, right? So that like as after you have enough number of updates, it will learn eventually that the right is the best action. But initially, as you see in the Q learning graph, here you are plotting number of as a function of episodes. Like after training the Q learning for this many episodes, with how many uh, actions, how much fraction of the left actions you are taking from state A. For Q learning, you see that the fraction of left actions is initially very high due to the maximization bias, and it will keep decreasing. It will keep learning better and better as time progresses. But as you see in the double Q learning, this maximization bias is solved to some extent so that it will quickly learn that the left action is a bad action in state A. Okay. So this is just one toy example to illustrate the advantage of double Q learning versus the conventional Q learning. Okay. Huh? So this is the behavioral policy which we are plotting. So behavioral policy is epsilon greedy with respect to Q, right? Q star, right? Here they have kept some constant epsilon 0.1. So this is not the target policy which they are plotting. They are plotting the behavioral policy. No, it if it was trained for few more iterations, maybe it will go down. Okay. So this is about Q learning and double Q learning. And maybe I'll also, since I have not showed you much examples, maybe I'll show you one more example where we are trying to compare, like we have looked at Monte Carlo methods and TD methods also, right? So let me just quickly show you some experiments on which is good. So this is another example which is trying to compare Monte Carlo versus TD methods. Like here the problem is the prediction problem which they are comparing. So this is the this is this is a problem in which they are comparing where once you fix the policy, you don't need to have the MDP, right, to understand about. So as I said, once you fix the policy, the MDP boils down to something like a Markov chain. Do you realize that? So let's say you have some. So let's say you have this. We what was the example through which we learn what an MDP is? Do you remember? In the initial classes, we learned what is Marco chain, what is MDP, right? What was the example we used? We used the example of gambling, right? Where you had some money and you have to decide how much money you want to put in the game, so that that will decide your next state. So let's say you had some 3 rupees money. An MDP will look like this, right? If you bet 1 rupee, where will you go? If you bet 2 rupees, where will you go? Right? So if you bet 1 rupee, what is the next state possible? Either 4 or 2, right? You are betting 1 rupee out of your 3 rupees, you will either go to 4 or 2. And let's say if you bet 2 rupees, you will either go to 5 or 1, right? So if you fix a like here you have actions and transitions also, right? But if you fix some policy, this diagram will boil down to some Markov chain, right? So let's say my policy is I will bet I'll always bet 1 rupee. That is my policy, right? So then this I can to just represent that policy. So my action will always be 1. So I need not draw these diagrams. All other actions I need not draw. So then it will just look like the diagram is from 3 you go to 4 with some half probability. From 3 you go to 2 with some probability half. Because I fixed my policy. My policy is that I'll always bet 1 rupee, right? So then for that policy, I just need to show this diagram, right? I don't need to show the full MDP to evaluate that policy. I have to just show this Markov chain, right? And maybe I should also tell you the reward also. Like in addition to that, I have to just tell you for this transition, what is the reward I'll get. Okay. So a Markov chain with just reward specification is called an Markov reward process. Okay. So once you fix the policy, you don't have to know the MDP to evaluate that policy. You just need to know the transition diagram for that particular policy, right? So this is clear for a deterministic policy. For example, if my policy is a stochastic policy, let's say my policy is I'll bet either 1 rupee or 2 rupees. Let's say with probability half, I'll bet 1 rupee. With probability half, I'll bet 2 rupees. So in that case, will it still boil down to a Markov chain or no? Is it clear what I'm asking? So I have this MDP. So I gave you the full MDP. Maybe there is another action also possible, which is 3. Like if I bet 3 rupees, then I'll either go to 0 or I'll go to 6. So this is the full MDP specification. Now my policy is, let's say I bet either half 1 rupee with probability half and bet 2 rupees with probability half. So will if I impose that policy, will that boil down to a Markov chain or not? If you are in state 3, so how will you calculate the transition probabilities? No, no. It will just depend on the current state only. Otherwise, how will it be a Markov chain? So if my policy is I'll bet probability of one action is half and probability that I'll bet 2 rupees is a half. Okay. Now, what is the probability that I'll go to? What are all possible states I'll go to from 3, 4 or 5, right? On the right side and 2 and 1 on the left side. So there are 4 possible states. Now for specifying a Markov chain, what all things I need to tell? I have to just tell probability of st plus 1 equal to 4 given st equal to 3. I have to tell this for all kinds of pairs, right? So if I give you the policy, this policy, can't you calculate this value? How can I calculate? So like what is the probability that I'll go to state 4 when I'm in state 3 while following this stochastic policy? I can calculate this, right? So it is just first, what is the probability that I'll take action 1 into the probability that I'll win the toss. So it will be 1 by 4, right? So the probability for going from 3 to 4 will be 1 by 4. Similarly, for all other, there are 4 possible states. For every state, the probability will be 1 by 4. So if you fix the policy, uh, you don't have to give you the, I don't have to give you the full MDP. I have to just give you the transition diagrams corresponding to the Markov chain, right? So why am I telling you all this? Because in this book, for comparing the Monte Carlo and TD for prediction problem, they have just specified this diagram without telling you the actions. Okay, so assume that they have fixed some policy already, and for that policy we are evaluating, which is like what is the value for that given policy. So I can just specify the Markov chain kind of a diagram with in addition to the reward for going into that state, what reward I'll get. Okay. So here they have a deterministic transition. I think so. If you are in D, if you uh, so here there are different possible actions. So it's a random walk. So if you are in some state D, the for the given policy, you will either go right with probability half, you will either go left with probability half. So that is the final Markov chain which we got for whatever policy they are following and whatever MDP they started with. So the Markov chain became like this. So if you are in status, the probability of going to right will be half, and the probability of going to left will also be half. And these are the rewards that you get for going to any of these states. So if you move among these states, you won't get any reward. The reward will be 0. And for transitioning from E to this terminal state, the reward will be 1. Okay. And for transitioning from here to here, the reward will be 0. Okay. So then uh, what is the value of some particular state? What is the value of state E? According to this policy, will that be 1? Will the value of state E be 1? Value of state means what? If you start from that state and follow that policy, what is the expected return that you'll get? Will V of E be 1? No, right? Why? Because with probability half, you'll go here, and with probability half, you go to the left, right? So the value of E will be the value of E will be 1 into half, because with probability half, you will go to the right, plus V of D into half, right? So if you just write these things properly, you will get this value function. You can mathematically find that the value function of these states will be 1 by 4, 5 by 6, 4 by 6, etc. Okay. Intuitively, the value of E should be higher than the value of D, right? Because if you start at D, the probability of getting more reward is higher, right? If you start at A, then you are most likely to end up in the left terminal state than the right terminal state. So you can just calculate these things mathematically. You'll get these as the true value for these states. For the given policy, these are the true values for these states. Okay. Now they have done some comparison between Monte Carlo and TD methods. After how many episodes will they converge to these true values? Like this is the V pi of, for some policy pi, this is V pi of A, V pi of B, all these things. Now we want to find these without doing this maths, right? We want to do it in the model free setting. Okay. So let me show you what those are. So this left one is for, this left graph is for the TD method which they are showing. So as I said, in the x-axis they are plotting the states, and y-axis is the value of that state, and this black line, uh, the black line which is a linear line, is the true values. Like as I mentioned, the true values are 1 by 5 and 2 by 5, so on 5 by 6, right? So that black curve is the true values, and the other color curves are after training them for so many episodes, what is the value function that we currently have, estimates of the value function that we currently have. Okay, so the red curve is after one episode, that is the prediction that we had, and after 100 episodes you can see that we are very close to the true values. Like the blue curve is very close to the uh, black black line, right? So after 100 episodes we are kind of close to the true values. Our estimates have become close to the true values. And they have shown this for some particular values of alpha, etc. Like as I mentioned, alpha is a small constant which we are multiplying, right, in our Monte Carlo updates. And these particular graphs are shown for alpha equal to 0.1. But if you have decreased alpha as a function of time, as I mentioned, for convergence to the true values, what is the condition we need on alpha? In yesterday's class we discussed, right? Alpha should be decreasing with time such that the sum will be unbounded, but the sum of the squares is bounded. Like 1 by t is one such example, like alpha t. If they have used alpha t equal to 1 by t, it will converge. But for this constant alpha equal, they have done this for constant alpha equal to 0.1, and they're saying that even after 100 episodes, if you still train it, it won't get any better than that, because the alpha is not satisfying the requirements of us, whatever we wanted. Okay. And on the right side, they are showing the performance of Monte Carlo versus TD. On the right side graph, they are showing the performance of Monte Carlo versus TD for various alphas. Like here also they kept the alphas constant, but you can see that as alpha, if you use a very small constant, it might converge a little slowly, but it will converge to a better estimate as time progresses. Right? You can see this, right? For example, for alpha equal to 0.5, this is the curve for t. Initially, when alpha equal to 0.5, the estimates are like they're plotting the error here. Like the error is the difference between the true values and the estimated values. Like x-axis is after so many episodes, what is the error? The error is the mean square error between the true values and the estimated values. Okay. So when you choose a small alpha, you initially your error might be high, but it will gradually keep getting closer and closer to your true values as the number of episodes increases. But a higher value of alpha might give you slightly better initial conversions, but after that it will kind of saturate. Okay. So that's why a decreasing size of alpha is a good value, because initially you have higher values of alpha so that it will bring you closer to the optimal values, and later you will keep decreasing your alpha so that it will continue to keep getting closer and closer to the true values, because it's a good trade-off, right? Because if you keep a very high alpha, you get closer very soon, but after that you kind of saturate, you don't get further close to your optimal values. But if you keep a very small alpha right from beginning, initially the convergence will be very bad. Like the convergence will not be very fast. So hence 1 by t kind of a thing is good, because initially you keep a higher alpha so that you come closer quickly, and then you try to decrease it so that you keep getting closer and closer. And theoretically, at least the authors mentioned that theoretically there is no clear winner between Monte Carlo and TD, but empirically, like there is no theoretical proof as to which is exactly strictly better than the other. But empirically, on many MDPs, they have observed that TD generally performs better than the Monte Carlo methods. Okay, as seen from this particular example also, like the TD method seems to perform better than the Monte Carlo methods, right? Within 100 episodes, the TD error is much lesser than the Monte Carlo errors. Okay, so this is just some plots to understand how close, like how to compare two algorithms, kind of a thing. Like you try to see after some episodes of training how much residual error is there, etc. You can compare. Okay, and in the assignment also you might have seen some comparison between SARSA and Q learning, right? So how many of you completed the assignment? I think the assignment is very simple, right? I was like I'm asking you to just code couple of lines, right? Uh, Maybe it's not challenging enough for you to try, yeah? Okay, so maybe I'll quickly run through that example as well. So uh, for the, like, as you might have read in the assignment, so here we are comparing the performance of SARSA and Q learning, where the plot here is trying to tell, like, as a function of number of episodes, how much reward are you getting, right? So like the reward is the negative, right? It's minus 25 here and minus 75. As you see, the SARSA is having higher, like, negative reward. I mean, the SARSA is performing slightly poorer than the Q learning. So what is the reward here for this problem? Okay. So what is this? Sums of rewards during the episode. Okay. So I think this could be the behavioral policy. Okay. So here, as so what does, if you keep a constant epsilon, what will SARSA converge to? Like, you remember the rules, like if you in Q learning, if you let's say I'll keep always use, let's say, point 0.1 greedy as the behavioral policy. Will Q learning, what will Q learning converge to? Like, is the question clear? So in the Q learning, we have only the choice to choose the behavioral policy, right? The target policy is always the greedy policy, right? So let's say I choose point 0.1 greedy as my behavioral policy in Q learning. What policy will it converge to? It will converge to the optimal policy, right? Why? Because in Q learning, what is the requirement for it to converge to the optimal policy? Greedy in the limit and infinite exploration. Those are the two things which we need, right? So Q learning target policy is already greedy, so that is satisfied. And infinite exploration, like zero point 0.1 epsilon, like zero point 0.1 greedy, like epsilon equal to zero point 0.1 is also satisfying infinite exploration, right? So that satisfies both the properties. So it will converge to the optimal policy. So what is the optimal policy in this thing? This is the red line, right? Like for every step, you get a -1 reward, I guess. And if you fall into the cliff, you get a minus 100 reward, right? So this particular path will lead you to the destination in the shortest path. And what will epsilon greedy converge to? Like, what will the SARSA converge to with a constant epsilon? Will it satisfy the properties of glee if I use a constant epsilon? What is the glee properties? Greedy in the limit. The target policy should become greedy in the limit, and you should have infinite exploration. So in SARSA, if I keep point 0.1 greedy always, will it satisfy both these properties? Which property will not satisfy? Infinite exploration is satisfied, right? Because with some probability epsilon, you are taking a random action. That means all state action pairs are explored enough. Greedy in the limit is not satisfied, right? Because you are keeping a constant epsilon equal to 0.1. So your target policy will always be 0.1 greedy. That means it will never go to greedy, right? If you keep epsilon equal to 1 by t, maybe as t tends to infinity, your epsilon becomes 0 and it will converge to a greedy policy. But if you keep a constant epsilon in the SARSA, the target policy will always be 0.1 greedy. So it will never converge to the optimal policy, right? I see a lot of blank faces. Are you understanding or not? Right? So, so it will not converge to the optimal policy. That is clear. But what will it converge to? Huh? It will converge to the best policy among epsilon soft policies, right? Among all the policies which will explore with let's say 0.1 probability, it will converge to the best policy. So if you look at all policies, let's say you keep epsilon equal to 0.1 constant in the SARSA. So you let's say you look at a policy which is so let's say it will converge to this optimal path. Let's assume that the Q function of SARSA converge to this red path. Then what will happen to the performance of that? Because it will always keep exploring with some probability 0.1, right? Because our epsilon is 0.1. So our target policy will keep exploring. So if you are in this state with some probability 0.1, you will go down. Like not 0.1, maybe 0.1 by 4. With probability 0.1 by 4, you will go down, right? So that means with probability 0.1 1 by 4, you are having a reward of minus 100, right? But if you look at this policy, with some probability 0.1 by 4, if it comes down, there is nothing to lose for it, right? Are you understanding what I'm saying? So if you look at the value, if you look at V pi, if you look at V pi for the policy, which is 0.1 greedy, then if you take this path and behave according to epsilon greedy, then with some chance, there is a lot of chance that you fall into the cliff. So there is a lot of reduction in the value of that policy. But if you are here, if you come down with some probability, there is nothing much to lose. Like the probability of falling into the cliff is much lesser for the blue path than the probability for the red path. So if you look at all the policies which will keep exploring with some probability, the red path is not the best path. Because if you always keep exploring with some probability, so there is always a chance of falling into the cliff, right? So the value of such a policy will be much lesser, because if you reach the goal, maybe you will get a reward of uh, like if you because you will get a minus 100 reward whenever you fall into the cliff. So if you go very close to the cliff and you keep behaving randomly with some probability, then there is a lot of thing to lose, right? So if you go very far, even if you behave randomly, the probability of going into the cliff is much lesser. So that's why the best policy among some epsilon soft policies will be the blue path, because if you predict the value of the blue path, the probability of going into the cliff will be much lesser. So it doesn't affect this minus 100 reward doesn't affect its value much, because maybe very rarely it will come into that cliff. Because if it has to come into the cliff, it has to do exploration here. It has to take exploration step here. It has to take exploration step here. So 3 times it has to take a random action for it to fall into the cliff. But if you are in the red path, just one random action will let you fall into the cliff. So the probability of falling into the cliff is much lesser for the blue path. So the probability of getting minus 100 reward is much lesser for the blue path. So the expected return for the blue path will be much higher if you follow according to epsilon greedy policy. Okay. If you No, Q learning is converging to the optimal policy because your Q learning is essentially the value iteration thing. So you are just using the Bellman optimality equation and keep updating all possible S comma S. So if you keep updating all S comma S enough, it will converge to the optimal policy, right? Because it will converge to Q star. No, it's already in every step it's greedy. So that's why it's also greedy. No, I am telling for any general TD method or any general greedy method, if your target policy satisfies this and the behavioral policy satisfies this, you will converge to the optimal policy. So Q learning is satisfying these two properties, is what I think. This is one way to argue. The other way is arguing from the Bellman optimality perspective. Okay. So is everyone clear why Q learning will converge to the red path while the SARSA will converge to the blue path? But if you keep decreasing epsilon in the SARSA, eventually it will also converge to the red path, right? Maybe you can try that as well in the assignment. Like you need not submit it, but you can look at it. Like if you keep decreasing your epsilon as a function of time, initially maybe it will learn a slightly safer path, but as epsilon keeps decreasing, maybe if epsilon is very, very small, maybe the red path is also fine because the probability of going into the cliff is so low that you don't have to be so safe. You don't have to play so safe. Okay. So I think here we are plotting when we are plotting this two curves below, we are plotting the behavioral policy, I guess. In the behavioral policy, the Q learning, we are using epsilon greedy, right, for the behavioral policy. So it will see more negative rewards. The Q learning, the behavioral policy will fall into the cliff lot of times. While it will learn the optimal path, but during the training, it will fall into the cliff a lot of times, the Q learning algorithm, because the actions you are taking according to behavioral policy, right? Your behavioral policy in Q learning is an epsilon greedy policy. So while during the training phase, the Q learning will have a lot of negative rewards because a lot of times it is going very close to the cliff and it will keep falling into the cliff, right? But if you plot once you learn after some episodes, once you learn, you fix that policy and just behave according to the policy which you learn, then Q learning will have a better reward, right? After you learn the Q, you won't behave epsilon greedy, right? Once you finish everything, you will learn some policy, you'll just follow that policy. So the Q learning would have learned this red path, it will just go in that red path. So the reward will be much higher. And for SARSA, it will keep exploring, so the reward will be lesser. I'm I'm not sure how many of you followed, but if there are any doubts, you can ask me. I'll explain. Any doubts in this particular thing? Like you understood why these graphs are like this? Why is the reward for Q learning the plot? The Q learning plot has lesser reward than the blue blue curve. Okay. Okay. So this is because I was covering a lot of algorithms, but I never showed you some experiments. So I just thought I'll show some experiments in today's class. Okay. So maybe I'll try to quickly cover one topic in today's lecture and we'll wind up. So in today's lecture, we'll cover this topic called model-based learning, model-based RL. So in yesterday's class, I briefly explained you what is model-based RL, right? Anyone remembers what is model-based RL? So so this Q learning, this SARSA, all these are called model-free algorithms because we are not explicitly learning what is PSS-A or RSA. Like these are the terms which will specify the model, right? Like the MDP dynamics is the model, right? So these two terms specify what is the MDP model. So we are not explicitly learning or estimating these two parameters in our SARSA or Q learning. We are directly trying to learn what is V pi or what is Q star or Q pi. We are directly learning these estimates of these values without explicitly estimating what is RSA or what is PSS-A, right? So that's why those are called model-free learning algorithms because you're not trying to learn what the MDP is. You're directly trying to learn what is your Q star or what is Q pi, etc. for a given policy pi. So in model-based RL, what we'll do is we'll try to learn these estimates also because you are interacting with the environment using some policy, right? Let's say in the SARSA, you start with some arbitrary policy, then you'll behave according to that policy, and then you keep improving, right? So during that interaction, you might have started with some state S naught, you might have taken some action A naught and got some reward, some next state. So you'll keep getting this episode. You will keep getting a lot of trajectories, right? You have a lot of experience uh, using your behavioral policy. You are taking the actions, and you will get a lot of episodes. So using this data, instead of just learning what is Q star or Q pi, you can also learn from this sample. What can I infer? Can I infer anything about? Let's say I see some sample like this, some tuple SA or S dash. I see some tuple like this. Can I get any estimates of RSA and PSS dash A based on this? Right. So this will just give me one sample of PSS dash A, right? If this is S, so if this is S dash and this is A, then I can update what is PSS dash A. This will give me one sample of PSS dash, right? So let's say you have visited that state S comma A a lot of times, and sometimes you went to state S, sometimes let's say you went to state S dash. So based on a lot of episodes, you got these three samples, let's say. You have come to the state S comma A three times, and you observe that once you went to state S dash and two times you went to state S double dash, based on your episodes of observations which you have. Based on this, we can predict what is PSS dash A, right? What will be PSS dash A based on this? With probability 1 by 3, it will be PSS dash A, and with SS dash will be 2 by 3, right? Based on this sample data. So based on your observations, you keep updating your estimates of the model. Okay. So as you see, whenever you see this state S comma A, you just update these probabilities. Okay. So let's say you come after some time, you come to this state again, and let's say you've seen S double dash, then you'd have updated these two to half and half after one more sample of based on these four samples, you would have updated them to half comma half, right? Because in two times you went to not half comma half, maybe if you have gone to S dash, it will be half comma half. You would have gone to S dash two times and S double dash two times. So it's just a trivial estimation of your model parameters based on whatever data you are seeing. Similarly, you can also update your RSA, right? So you just see. how many times you visited status and took action A, and during those times, what are the rewards that you got? You just collect all that data, and you just take the average of all those rewards that you got whenever you are in status and took action A. That will give you an estimate of RSA, right? Like in sometimes you got, let's say point 0.1, sometimes you got point 0.3, sometimes you got point 0.7. Whenever you visit status, then you will just take the average of these three rewards, which will give you your estimate of RSA will be just 1 by 3, right? If you have seen these three observations, your estimate of RSA will be 1 by 3. So like that, you not only learn about the Q star, but will also keep updating RSA and PSS-A based on whatever observations you are seeing while you are interacting with the environment. So how will you use these estimates now? Yeah. Yeah. So like you have to do this. Yes, A, S dash, all possible S dashes, you have to keep updating those probabilities. So for every state S comma A, you maintain this table. Like for every state S comma A, you write down what are all the next states and how many times you visited those next states. Based on that, you compute these things, and based on this, you compute RSA. So you just compute these online. Like whenever you see some state S comma A, you update these two parameters, RSA and PSS dash A. So now what we'll do is, because sometimes interaction with the environment might be costly, right? You might be using some device, like you might have to pay, or let's say you're doing some testing with some robot or some car. All getting real-time experience might be costly, right? So you might have only finite time with the device which you are trying to learn about. So instead of just learning about Q, you also try to learn how the device behaves, how the environment behaves by estimating these two parameters. Now, instead of just relying on the actual interaction with the environment to update your Q values, you also, based on your model, you can also improve your Q values, right? So if you have access to these two parameters, then we know how to do the find the optimal Q star, right? How can we do? We can use methods like policy iteration or value iteration if you already know the model. So what we'll do is, there is an algorithm called DynaQ which tries to club this model based method and the model free methods. Like the model free methods, one algorithm we have seen is Q learning, right? So whenever you encounter some state st comma at, we'll just update that particular Q of st comma at. So based on every sample, you just update your Q function once, right? So instead of just doing that much, what you'll do is you will do this update once with the real-time interaction. With the real-time interaction, you would have got something like this, right? So you'll, based on this target, you'll update your Q learning once. The actual like Q new, Q old, you add all that here. Like you do the normal Q learning update once, and instead of just stopping with that, what you'll do is you do the actual update with the Q learning based on your real interaction once, and then you do some 10 updates for the Q based on your sample interactions. Like you simulate the interaction with the environment. You don't actually interact with the environment in real time, but based on these parameters, you can simulate, right? So let's say you are in some state ST and you took action AT. If you actually interact with the environment will give you RT plus 1 and ST plus 1. But instead of actually interacting with the environment, you use your model estimates to predict, to simulate what will be RT and what will be ST plus 1. You can simulate these two, right? Because you have learned what is PSA and RSA. Based on this, you can simulate what is this. You just generate one sample from this distribution which you have learned, right? And based on this transition probabilities, you simulate some state st plus 1. You can simulate the trajectory, right, without actually interacting with the environment. Just use these two parameters to just generate a simulated experience, simulated episode. So based on that simulated episode also, you can update your queue. You just think of it as if you are actually interacting with the environment and keep updating your queue function. So for every maybe for every one actual interaction with the environment, you update your queue based on the actual interaction once, and maybe you can simulate some 10 more steps based on your estimated parameters. You just generate the simulated experience, and based on that also you update your queue. Okay, so this is called uh, this particular idea is called dyna-queue algorithm. Okay, so where you are actually interacting with the environment once and updating your queue, and then you are simulating your episode and interacting with the environment. Like without interacting, you just simulate and generate some episode, and based on that also you update your queue, so that your conversions might become faster. Because once you have reasonable experience with the actual interaction, your estimates of these model parameters will be more or less reasonably good, right? Let's say after some 100 episodes, you might not actually converse to q star, but you would have got some reasonably good estimates of your model parameters. So this simulated data will also help you improve your q estimates. No, we are not saying these values will converge first. It's like you're doing both these things parallelly. So for every one interaction with the environment, you are doing some simulated experience. No, both of them have similar kind of information, but here you are extracting more from that same information. Here you are just using that episode once, right? Here, like this, you have generated some SA S dash R. You are just using this episode only once, but by using that here, you are reusing that information more effectively. Yeah, yeah. So what? No, like you can estimate the property distribution also, right? If you want, because you are seeing whenever yeah, you can estimate the distribution if you want, or you can just estimate the average and always use that average in your Q function. Update RSA, you just use RSA. You don't update the model. You won't update because you are not getting any more new data. So you'll freeze the model. Only you will update the model through actual interaction. With the simulated experience, you only update your Q function. Okay. So maybe I'll just show you. So this is just some quick empirical example to see the advantage of using both these things, like both the simulated experience as well as the real-time interaction. So the simulated experience, whatever you do based on the simulated experience, the book refers that as planning. The book calls it as planning because you're not learning. Learning is generally used for actual interaction with the environment, and planning is what they are using for the simulation. Okay, So here they have taken this grid example with uh, same what the same grid kind of an example which we have before. Like there's some start state and end state, and the four actions, etc. And here the blue curve corresponds to just doing the conventional Q learning without any simulation. You just update based only on your actual interaction with the environment. And as you see, like here on the x-axis, they are writing episode numbers. On the y-axis, they are writing how many steps, after how many steps you reach the goal. Okay. As you see, the blue curve initially it is taking around 800 steps to reach the goal. Like you can think of it as the reward. Like because if you take -1 for every step, it's like -800 reward, and eventually it will after some 30 episodes. You can see that the blue curve after some 30 episodes, the blue curve has a reward close to -14. Like 14 steps, it is converging. So maybe the optimal path from the start to goal is around 14. So after around 30 episodes, it is converging to the 14 steps. But as you see, when you use 5 planning steps, the green curve, it is converging to the optimal policy much quicker than the blue curve. And in the red curve is also with 50 simulation steps per every interaction with the actual environment. 1:50 ratio. For every interaction with the environment, you do 50 uh, updates of Q for the simulation. So this is just a quick empirical observation to see that the simulation model, estimating the model and using the simulation experience also to update your Q learning, update your Q estimates helps us. Okay. Yeah, this is about DynaQ. There are few details which I'm not going in very much detail, but roughly that is the idea. You just based on your simulate interaction, you update your model, and with whatever model you have, you simulate some episodes, and you update your queue both with the actual interaction and with the simulated experience as well. Okay, and this will help us in a slightly faster convergence. Okay, yeah, that's all. Thank you.